The early days of 1943 in North Africa were a harsh, bloody lesson in asymmetrical warfare for American tankers. Imagine being inside the turret of an M4 Sherman, knowing you were entering a fight where the odds were stacked brutally against you. The German Panzer IVs weren't just tougher, they were snipers. They could reliably punch through the Sherman's frontal plate from a terrifying 1,500 yards away. Meanwhile, American crews had to risk closing the distance to what felt like spitting distance, maybe 500 yards, just to have a chance of scratching the enemy paint. The result was heartbreaking and strategically disastrous. For every single German tank the Allies managed to eliminate, the US was losing 3, sometimes even 4, Shermans. This kill-loss ratio was simply unsustainable, and with the inevitable invasion of Europe looming, the clock was ticking for the army brass to find a genuine solution. The typical, knee-jerk reaction would have been to demand thicker armor and bigger guns, essentially creating slow, heavily armored fortresses. But Brigadier General Andrew Bruce, the commanding genius behind the Tank Destroyer Command, saw the problem through a completely different lens. He had meticulously studied the devastating success of the German blitzkrieg tactics, and he realized that armor wasn't the answer. Bruce recognized a universal truth: even the fearsome Tiger and Panther tanks had soft spots. While their front armor might be nearly impenetrable at 100 mm thick, the sides and rear were drastically thinner, often only 80 mm. His radical, almost terrifyingly simple, concept was born: stop trying to slug it out face to face. Instead, use overwhelming speed to bypass the enemy's strengths and hammer their weaknesses. This doctrine was swiftly codified as shoot and scoot, get in fast, deliver a lethal blow to the vulnerable flanks, and vanish before the enemy could even pivot to return fire. This wasn't just a tactical shift, it demanded a revolutionary change in vehicle engineering. Speed stopped being a bonus and became the core survival mechanism. In February 1943, Bruce's team defined the specifications for this new weapon, and they sounded utterly absurd to engineers at the time: a vehicle that needed to scream down roads at 50 miles per hour, maintain a dizzying 35 miles per hour cross-country speed, carry a heavy 76 mm anti-tank gun, and yet somehow remain light enough not to collapse temporary bridges. For comparison, the reliable old Sherman struggled to hit 25 miles per hour and felt like it was disintegrating at that pace. Bruce was demanding double the performance. He had calculated that this velocity would allow his tank destroyers to respond to German advances 3 times faster than standard armor, ensuring they were already dug into ambush positions long before the panzers arrived. The requirement was clear: they needed a vehicle that could genuinely fly across the battlefield at highway speeds. The only immediate obstacle: no tank engine. The requirement for a vehicle that could fly across Europe at 50 miles per hour presented an impossible engineering hurdle. The standard engine of the day, the reliable Continental R975 radial that powered the M4 Sherman, was already working overtime just to push 33 tons of tank around, delivering a respectable but maxed-out 400 horsepower. The Hellcat needed to be significantly faster while still hauling a crew, a heavy 76 mm gun, and enough ammunition to actually fight. Conventional power plant mathematics simply failed to compute. This is where General Motors' Buick division stepped into the story, and their solution was nothing short of radical. Instead of trying to beef up a truck engine, Buick's engineers looked skyward. They adapted the Wright R975 Twin Cyclone 9, an engine originally designed for aircraft. This aviation powerhouse was tuned to consistently deliver 450 horsepower and, critically, it had an unparalleled power-to-weight ratio, weighing in at only about 1,500 pounds, light enough to make automotive engineers absolutely giddy. In April 1943, Buick officially received the contract to convert this magnificent aviation machine into a ground pounder. But sticking an airplane engine into a tank is much harder than it sounds. Plane engines thrive running cool, smooth, and constant at high altitude. Tank engines, however, must endure brutal stop-and-go combat, lugging through mud, climbing steep grades from a standstill, and idling for hours during ambushes. Chief Engineer Charles Chain and his team had to redesign nearly everything. The most immediate challenge was cooling. Radial engines rely on the massive airflow generated by a propeller to keep from overheating. Inside a sealed engine bay. Zero airflow. Buick solved this by installing two enormous, 11-blade cooling fans designed to move 10,000 cubic feet of air per minute through the compartment, ensuring the engine stayed cool even when the vehicle was stationary. Next was the fuel delivery. Aircraft often use gravity feed, but a tank might be climbing hills at a terrifying 45-degree angle or tilting precariously sideways. The solution was a sophisticated, pressurized fuel system featuring multiple redundant pumps that guaranteed the engine was fed regardless of the Hellcat's orientation. Finally, they conquered the oil circulation problem, where radial engines traditionally rely on specific positioning, by designing a high-capacity dry sump system with external reservoirs, guaranteeing lubrication even when the M18 was practically standing on its nose. By July 1943, they had achieved the impossible, a working prototype engine that continuously pumped out 450 horsepower, capable of maintaining maximum output for 6 straight hours, far longer than any realistic combat engagement. So, what did that incredible power-to-weight ratio actually mean in the field? We're talking about 25.4 horsepower for every ton of tank, a truly staggering number when you look at the competition. The venerable Sherman tank only managed 12.1 horsepower per ton, and even the fearsome German Panther could only boast 15.4. This wasn't just a minor improvement, this was the American strategy crystallized, winning through overwhelming mechanical agility. But here's the rub, 450 horsepower is useless if you bolt it onto a 40-ton brick. The entire M18 design was built around one brutal, uncompromising truth: weight is the absolute enemy of speed. Every extra pound was a direct reduction in the Hellcat's primary advantage, its mobility. Buick's engineers faced a dilemma that bordered on the impossible: how do you give a crew enough protection to survive machine gun fire and shell fragments without tipping the scales and turning the vehicle into a sluggish target? Standard American tank armor, the rolled homogeneous steel used on the Sherman, was thick, often 50 to 75 millimeters on the front glacis. If the M18 had been armored to those specifications, it would have immediately ballooned to 35 tons and wouldn't have been able to crack 30 miles per hour. This necessity forced a radical choice, one that military historians have debated for decades: they gutted the armor. The Hellcat's protection was slashed to an average thickness of just 12.7 millimeters, with the thickest frontal plate maxing out at a mere 25 millimeters. To visualize that, 25 millimeters is roughly the height of 3 stacked U.S. quarters. Yes, a German 88 millimeters cannon could punch through that thin shell from miles away as if it were tissue paper. However, the brilliance lay not in the thickness, but in the shape. The team didn't just make thin armor, they made smart armor. Every single plate on the M18 was sloped at 45 degrees or greater from the vertical. When a projectile slams into angled armor, it must travel through far more material to penetrate, a concept called effective thickness. That 25 mm frontal plate, angled at 45 degrees, offered the defensive equivalent of 35 mm of straight-up vertical steel. The engineers obsessively studied German shell trajectories, angling the glacis plate at 50 degrees and the turret front at 45 degrees to maximize the chance of a ricochet, even giving the hull sides a slight outward tilt. They paired this structural cunning with revolutionary material choices. They didn't use pure steel everywhere; wherever load requirements allowed, they incorporated aluminum components. This was the game changer. Components like the transmission housing, the engine deck access panels, and internal bracing were made from aluminum alloy 356, which provided 60% of steel's strength while weighing only a third as much. The road wheels were aluminum, the entire rotating turret basket where the crew stood was aluminum mesh, and even the framing for the ammunition racks was designed for minimal mass. This fanatical dedication to shedding weight saved approximately 2.3 tons compared to traditional all-steel construction. Finally, the turret itself, unlike the boxy shapes of its contemporaries, was cast as a smooth, rounded, almost aerodynamic shape. That sleek, rounded shape wasn't just for looks, it was pure science. When engineers ran the M18 through wind tunnel tests at the GM Proving Grounds, Yes, they put a tank destroyer in a specialized wind tunnel. The results were stunning. The highly streamlined turret and hull dramatically cut aerodynamic drag by 18% compared to the boxy, angular designs of its contemporaries. What did that mean in a practical sense? At the Hellcat's top speed of 55 miles per hour, the engine wasn't fighting as hard against the air. This efficiency translated directly into better fuel economy and reduced engine strain, stretching the operational range from a meager 125 miles to a much more respectable 150 miles on the same tank of gas. The culmination of all these weight-saving measures, the thin, angled armor, the extensive use of aluminum, and the compact design, resulted in a fighting vehicle that tipped the scales at a mere 17.7 tons when fully loaded with crew, fuel, and ammunition. To put that figure into perspective, this vehicle weighed less than half of a standard M4 Sherman tank. This extreme lightweighting immediately created a split in opinion. Was it a brilliant, agile weapon, a scalpel, as its supporters claimed? Or was it a flimsy, high-speed coffin, a death trap, as the critics worried? Both views held merit. The engineers knew that having all the horsepower in the world and a feather-light chassis meant nothing if the transmission exploded the first time the driver stomped the accelerator. This single component was the silent killer of most high-speed armored prototypes of the era. The stress of translating raw engine power into actual, reliable movement destroyed the mechanical components. The Hellcat demanded a gearbox that could absorb massive shock loads, handle sustained highway speeds, tolerate constant, aggressive gear changes in the heat of battle, and even permit an emergency full-throttle reverse when ambushed. General Motors assigned this monumental engineering task to their Hydromatic division, the same team that had successfully brought reliable automatic transmissions to civilian cars just 5 years prior. However, designing a transmission for a 17-ton tracked vehicle that could accelerate from 0 to 30 miles per hour in under 15 seconds required solving problems far beyond those faced by passenger sedans. The torque loads were astronomical, and overheating was a constant, dangerous threat due to the sheer friction generated by tracks. Their ingenious answer was the Torquematic transmission, a design legitimately decades ahead of its time. Instead of the crude, manual crash boxes that required exhausting double clutching and driver finesse, the Torquematic was a semi-automatic, 3-speed system centered on a crucial component, the torque converter. Think of the torque converter as a fluid-filled cushion situated between the engine's explosive power and the rigid mechanical gears. This fluid coupling absorbed all the violent shock loads, preventing the drivetrain from tearing itself apart during aggressive maneuvers. It allowed the driver gentle, smooth control at slow speeds, preventing stalls, but when the crew needed maximum acceleration, the converter locked up, transferring nearly 100% of the engine's power directly to the tracks. This dual-mode operation meant even fresh, relatively unskilled drivers could operate the Hellcat smoothly, while expert crews could extract maximum, sustained performance. That performance potential was locked into 3 perfectly calibrated gears. First gear was essentially a climbing gear, giving the Hellcat the torque needed to scale a 60% gradient, a slope so sharp you're basically looking straight up a wall. Second gear was the bread and butter setting, allowing the driver to hold 25 to 35 miles per hour across rugged fields and broken ground without rattling the crew's teeth out. But the real magic was third gear, the high-speed cruiser. This allowed sustained 50 miles per hour runs on smooth European roads, keeping the engine happily humming around 2,400 revolutions per minute, right in its sweet spot for fuel efficiency. To keep things running smoothly and quietly, they chose helical-cut gears. Unlike the straight-cut gears common in older tanks, which produced a high-pitched, screaming whine that sounded like tortured metal and drove crews crazy, the helical teeth meshed gently at an angle. This distributed the immense load more evenly and drastically reduced noise, turning a potential banshee into a relative whisper. Of course, all that power generation creates immense heat, especially within the transmission fluid, which needed cooling immediately. The solution was simple and effective. A dedicated oil cooler mounted in the direct airstream right behind those giant engine fans. Transmission fluid was constantly pumped through aluminum fins, ensuring heat dissipation even during extended, flat-out sprints. When they tested this system in the brutal 100-degree heat of the Mojave Desert in August 1943, the Hellcat ran wide open for 2 hours straight, longer than it could even hold fuel, without overheating the transmission. The result? A reliability rate exceeding 98% during testing. This transmission was tough, failures were practically non-existent, even when subjected to battlefield-level abuse. Now, let's consider the problem this reliable speed machine created. You have a 17-ton vehicle capable of tearing across bomb-cratered French farmland at 55 miles per hour. If you just bolted conventional axles underneath, the forces generated would tear the Hellcat apart. Every bump, every dip, every railroad track crossed at speed translates into a massive vertical shock wave trying to dismantle the chassis and turn the crew's internal organs into mush. At slow speeds, suspension is about comfort. At 55 miles per hour in a combat zone, it's purely about structural integrity and survival. The engineers knew this, and their choice of suspension was pivotal, the torsion bar system. This design was the absolute key to the Hellcat's high-speed ability. Instead of bulky coil or leaf springs, which consume valuable hull space, the torsion bar uses long, high-strength steel rods anchored firmly to the chassis at one end. The other end connects to the swing arm holding the road wheel. When the wheel hits an obstacle, the swing arm rotates, twisting the steel rod along its length. The steel's powerful, inherent resistance to this twisting motion provides the necessary spring force to push the wheel back down. This system is brilliantly compact and progressive. The harder you twist it, the stiffer it fights back, which prevents the vehicle from violently bottoming out on harsh impacts. The M18 utilized 6 dual bogies per side, each protected by its own independent torsion bar, crafted from heat-treated chrome silicon alloy steel, capable of lasting well over 5,000 miles under punishing conditions. We had those incredible torsion bars, long, 4-foot steel rods, 1.5 inches thick, calibrated perfectly, with the front set slightly softer to absorb initial impacts and the rear stiffer to manage the weight transfer during hard acceleration and the violent kickback of the main gun firing. But even the best steel springs can turn a fast vehicle into a chaotic trampoline. Imagine hitting a deep pothole at 55 miles per hour, the vehicle would just bounce and oscillate repeatedly, making the gunner useless and physically exhausting the crew. The engineers knew they needed immediate control. So, they bolted heavy-duty hydraulic shock absorbers, functioning exactly like those in high-performance race cars, onto the frontmost and rearmost road wheel stations on each side. These shocks were the essential dampeners, designed to instantly kill those violent oscillations. The result was phenomenal. The Hellcat could literally drop 2 feet at full speed, and the crew wouldn't suffer whiplash, nor would the main gun slam against its elevation stops. The ride quality wasn't just about the springs and shocks, though. The tracks themselves played a crucial role. The M18 rolled on wide, 16-inch center guide tracks fitted with thick rubber chevron pads. That rubber was genius because it significantly lowered the ground pressure to a mere 10.7 pounds per square inch, meaning the Hellcat could float across mud and soft ground where heavier tanks would instantly bog down. Crucially, those rubber pads soaked up the high-frequency vibrations that usually rattled a tank crew's teeth loose. This wasn't just theory, testing proved it. During trials at Aberdeen in late 1943, the M18 prototype was thrashed over obstacles, including 18-inch trenches and vertical walls, at maximum speed. Even during the worst impacts, the measured vertical acceleration inside the crew compartment stayed below 2 gs. Crew testimonials backed this up, reporting they could maintain a comfortable 40 miles per hour over terrain that forced the standard Sherman tank to crawl along at 15 miles per hour. This superb stability meant the gunner could reliably keep the target locked down even while moving fast, directly translating into a vastly improved first shot hit probability. All of this technical mastery, however, was useless until it faced actual combat. The M18 Hellcat arrived in Europe in the summer of 1944, just after D-Day, and the initial reaction from the tankers was pure dread. Accustomed to the Sherman's thick hide, they saw the Hellcat's thin armor and assumed they'd been handed a fragile death trap. But that skepticism was about to evaporate completely in September 1944, near a small French town called Hellcat, where the true combat value of speed and firepower would finally be proven. The moment of truth arrived quickly. The Battle of Hellcat exploded on September 18, 1944, marking a massive German counteroffensive designed to slam the brakes on General Patton's rapid push toward the Reich. The enemy wasn't messing around. They committed the veteran 5th Panzer Army, including elements of the 11th Panzer Division, bristling with the dreaded Panther tank. These Panthers were terrifying beasts, packing a high-velocity 75mm cannon and protected by sloped frontal armor that rendered most American weapons useless at range. On paper, any meeting between these German heavyweights and the thin-skinned Hellcats should have been a slaughter favoring the enemy. But the 704th Tank Destroyer Battalion, attached to the 4th Armored Division, wasn't interested in playing fair. Lieutenant Edwin Leiper, commanding a platoon, detailed the flawless execution of their unique doctrine, speed over steel. The German column, confident and expecting a typical American frontal defense, advanced down a main road. The Hellcat crews, however, utilized the very speed the engineers had built into their machines. They roared off the main artery, tearing through dusty side roads and farm tracks to race into perfect flanking positions. They were perpendicular to the German line of advance before the Panther crews even realized they were being outmaneuvered. This move was everything. The Panther's strength was its nose, but its weakness was its side armor, a mere 40mm. The Hellcat's high-velocity 76mm gun, firing specialized M93 armor-piercing rounds, could punch straight through that flank from a staggering 1,200 yards away. The Germans never got a chance to use their superior frontal protection. The results were astounding. Over 3 days around Hellcat, the 704th Battalion reported demolishing 39 enemy tanks while losing only 7 of their own, a decisive 5-to-1 kill ratio against supposedly unbeatable German armor. Staff Sergeant James Brown's crew famously took out 3 Panthers on September 19. Imagine the scene: they were tearing across an orchard at 45 miles per hour, sliding to a stop behind a stone wall, blasting the lead Panther's turret ring twice, and then immediately peeling out to avoid return fire. Brown called it, "shoot, scoot, survive," and they repeated that deadly ballet 3 times in just 12 minutes. Beyond flanking, speed was a vital lifeline. Captain James Leach recalled receiving coordinates for an enemy concentration. While a Sherman unit would have needed up to half an hour to respond, his platoon covered 8 miles of French countryside in a blistering 11 minutes. They arrived on September 20 just in time to ambush a group of Panzer IVs that were still struggling to deploy into attack formation. The Germans, calculating their timing based on the predictable pace of Allied units, were caught utterly flat-footed. Yet, even the Hellcat couldn't cheat death forever. Near Rancourt on September 29, one unlucky platoon found themselves exposed in an. That brilliant record of shoot and scoot wasn't foolproof, however. Near Russia on September 29, the luck ran out entirely. A Hellcat platoon found itself completely exposed in an open field, pinned down by German anti-tank guns that were expertly dug in. Before the crews could react, 2 vehicles were instantly taken out. This was the brutal truth of the design. The thin armor that made them so blindingly fast became a fatal flaw the moment surprise and maneuverability abandoned them. The only reason the remaining vehicles managed to escape was that signature acceleration, hitting 40 miles per hour in mere seconds, creating enough distance and kicking up enough dust to break the German gunners' line of sight before they could finish the job. The lesson from that narrow escape was stark. A Hellcat's very existence depended on absolute mobility and the total avoidance of a fair fight. These dramatic combat results, spanning from the successes at Hellcat to the harrowing failures near Russia, ignited a searing debate that echoed through the mess halls, the command posts, and eventually dominated post-war military analysis. The fundamental question never went away: was sacrificing armor for speed truly a good bargain? Or had the military created a vehicle that only proved effective when battle conditions were precisely perfect? Crew opinions fractured based entirely on their personal experiences, with both sides possessing compelling arguments forged in blood and fire. The Hellcat enthusiasts pointed straight to the statistics, and they were undeniably persuasive. By the close of the war in Europe, M18 battalions had secured the highest kill-to-loss ratio of any American armored fighting vehicle, destroying an average of 2.4 German tanks for every Hellcat lost. The 704th Tank Destroyer Battalion alone ended the war with 136 confirmed enemy kills against only 17 losses. Staff Sergeant Carl Anderson, serving with the 705th, captured the sentiment plainly in 1945, "I'll take speed over armor every single time. You can't shoot what you can't catch, and the Jerrys couldn't catch us." Crews loved the ability to control the terms of engagement, striking the enemy when and where they chose, then vanishing before effective counterfire could be aimed. This speed was also a huge asset defensively. When German counterattacks successfully broke through American lines, Hellcat platoons could instantly redeploy to threatened sectors far faster than any other armored unit. During the critical Battle of the Bulge in December 1944, the 705th TD Battalion famously covered 45 miles through a punishing snowstorm in under 3 hours, arriving just in time to stop a German armored spearhead pushing toward Bastogne. This kind of strategic mobility meant that a handful of Hellcat battalions could effectively cover a frontage that would typically require twice the number of conventional tank units, a flexibility commanders valued immensely. But speak to the crews who had actually taken a hit, and the story changed immediately. The hull armor, just 12.7 mm thick, offered no protection whatsoever against German 75 mm or 88 mm main guns, and even heavy machine gun fire could punch through at close quarters. Lieutenant Robert Ankeny experienced this horror firsthand when his Hellcat took a direct hit from a Panther during the savage fighting in the Herten Forest in November 1944. The shell passed clean through the frontal plate, instantly killing the driver and bow gunner, turning the entire crew compartment into a raging inferno within seconds. Ankeny, who had been tossed clear of the resulting inferno, survived with terrible burns, but the cost of that speed over protection philosophy was 4 irreplaceable friends, incinerated in seconds. His post-battle assessment was brutal and raw: speed doesn't mean squat when you're caught. That thin armor is a death sentence. This deep-seated fear wasn't unique to him. The psychological weight of fighting in what many crews felt was simply an armored coffin was immense. Compounding the issue, the open-top turret, though great for situational awareness and rapid ammunition handling, meant that even glancing threats, like artillery air bursts or enemy grenades, could kill the crew instantly without the shell ever penetrating the hull armor. The mental strain reached a breaking point during the fierce fighting in the Khmar Pocket in January 1945, where several Hellcat crews actually requested transfers to slower Sherman units, willing to trade their speed advantage for the simple psychological comfort of thicker steel and an enclosed fighting compartment. When veterans and new recruits held fundamentally different definitions of acceptable risk, unit cohesion inevitably suffered. Furthermore, the very doctrine the M18 was built upon often failed its crews. General Bruce's shoot and scoot concept envisioned tank destroyers held in reserve, dashing out for flanking ambushes. But the grim realities of the battlefield frequently forced Hellcats into static, frontal engagements, supporting infantry or holding defensive lines, where their mobility was useless, and the armor trade-off became a fatal liability. After-action reports from the Italian campaign clearly showed disproportionate losses whenever the M18 was used in static roles, proving the engineers' initial warnings correct. Yet, when the guns finally fell silent in May 1945, the M18 Hellcat's combat scorecard was impressive. Out of the 526 minutes and 18 seconds deployed in the European theater, they destroyed over 1,000 enemy vehicles, achieving one of the lowest loss ratios among all American armored fighting vehicles. Crucially, the Hellcat's true legacy was not just its wartime performance, it was how profoundly it recast the future of armored doctrine for the next 4 decades. The moment the Soviet Union unveiled the T-54 in 1947, followed by the T-55, Western militaries faced the daunting problem of overwhelming numerical superiority. If the Soviets could field 3 tanks for every one NATO built, how do you beat superior numbers? The answer increasingly echoed the Hellcat's original formula: prioritize speed, heavy firepower, and tactical mobility over raw, heavy armor protection. The French AMX-13 light tank, developed in the late 1940s, became a direct spiritual successor, weighing only 15 tons, capable of hitting 60 km per hour, and packing a powerful 75 mm gun. The operating philosophy was identical: hit first from an unexpected angle, then relocate before the enemy can effectively respond. The combat lessons learned from the M18 were not simply archived, they fundamentally reshaped American armor doctrine almost immediately. Look no further than the M41 Walker Bulldog light tank, which arrived on the scene in 1951. This machine was the Hellcat spiritual successor, designed specifically to prioritize rapid reconnaissance and flanking maneuvers, rather than attempting to engage Soviet heavy tanks in a head-on brawl. But the engineers didn't stop there. They took the concept to its logical, almost absurd, extreme with the M56 Scorpion airborne anti-tank vehicle in the 1950s. The Scorpion was practically a bare-bones gun carriage, a massive 90mm cannon bolted onto a lightweight chassis with virtually no armor at all, built to be airdropped and then raced to defensive positions at a blistering 45 miles per hour. This was General Bruce's shoot and scoot doctrine distilled into its purest form, updated for the jet age. Even the Soviets were paying close attention. They carefully studied the effectiveness of speed-based flanking attacks in battles like Aracourt, recognizing that mobility could neutralize the technological advantages Western nations held in fire control. Their response was the ASU-85 airborne assault gun, introduced in 1959. While heavier than the M18 at 15.5 tons, it still managed 45 km per hour and packed an 85mm main gun designed specifically to execute those critical, unexpected flanking maneuvers against NATO armor. The ancient debate between armor and mobility never really concluded, instead, it evolved. Modern main battle tanks like the M1 Abrams seem to have achieved the impossible by blending massive protection with immense speed, but that's a luxury afforded by 2,500 horsepower gas turbines and composite armor that weighs a fraction of equivalent steel. Yet, when you look at vehicles designed for rapid deployment today, the Stryker MGS, the Italian Centauro, the Japanese Type 16, they are all singing directly from the Hellcat's hymnbook: light armor, substantial firepower, and systems optimized for immediate speed, designed to attack from angles the enemy isn't covering. Perhaps the M18's most enduring legacy is its ultimate proof that engineering constraints can actually drive profound innovation rather than limit it. The team at Buick didn't have magical materials or endless resources. They faced clear physical limitations. They couldn't build a vehicle that was simultaneously fast, heavily armored, and powerfully armed. So, they made the difficult trade-offs and ruthlessly optimized for a specific tactical niche. That discipline, that willingness to accept vulnerability in exchange for absolute dominance in speed and surprise, is the core lesson that echoes through every successful rapid deployment weapon system designed since. The crews who fought in those thin-skinned vehicles prove that, ultimately, the best armor is often not being where the enemy fires.